All right, it's critical when we talk about biomechanics to know terminology. Now, this terminology sheet is available, and I always post this in any biomechanics class I teach. And it's important just to be able to quickly go through all these terms, identify the definition of the term, identify an equation that's associated with the term where appropriate, and identify units where appropriate. And you should be able to go through this list really quickly. Not in a rushed way, but just no hesitation in defining these terms. Because as we start working with applying biomechanics to understand performance, we need to know the definitions of these terms, and we need to use them all the same way. And that way we can talk to each other about some of the details of performance. So I'm not going to go through each term now, but I will highlight some terms that you want to make sure you really understand as we head into the final. Displacement, distance, those are describing change in position. There's equations for each of those. Velocity we've used quite a bit. Speed we use as magnitude, the velocity vector. All right, remember velocity is a vector, has magnitude and direction associated with it, describes rate of change of position. Acceleration, we've used that quite a bit, rate of change of velocity, A equals delta V over delta T. Absolute angle and segment angle, we haven't used these, or relative angle, we haven't used these too much other than describing the angular position of, for example, the knee or the arm during swimming. And we have talked about the different ways to represent the angle. And when I talked about joint powers, I spent a little bit more time on angular position. So absolute angle and segment angle are the exact same thing. And it represents the angle of a segment relative to some fixed reference line in space. And then we have to define the reference frame, in essence, what is a zero angle and what direction of rotation an increase in angle represents. Relative to the angle is the angle between two anatomical segments. That would be a joint angle. So elbow, knee, hip, what have you. Angular velocity, we talked about, especially with biking, how fast angular position is changing. Angular speed, again, speed would be the magnitude of the velocity vector. Velocity is a vector, has magnitude and direction associated with. Speed is a scalar. Angular acceleration, we talked about when we started talking about torques and joint moments. That's rate of change of angular velocity. Force, we've used a lot. Tendency to cause a force is a push or pull that tends to cause motion, doesn't have to cause motion. Units of newtons. And I should have gone back up here. When we've used angular acceleration, even the velocity and even angle, the units that we use when we start going beyond understanding PV&A are radians. And so you want to understand what a radian is so that it's easier to understand the math as we go deeper into applying angular kinematics to understand angular kinetics. So radians are just a set of units to represent angular position. And in essence, they are unitless. So when we start doing our unit analysis, they drop out of our unit analysis. So there's a lot of advantages to using radians going forward instead of degrees. Inertia, we haven't used it specifically, but it does come in when we start talking about mass of an object. Represents the resistance to change motion, and it's again measured by mass of the object, and its units are kilograms. Impulse, we haven't talked too much, but it's good to know. It's represented by the product of force and time, or in the angular impulse direction, it's the product of torque and time, how long that torque is being applied. This starts to get important when we want to understand change in momentum, which is quantity of motion and is represented by the product of mass and velocity. We spent some time on torque when we were looking specifically at cycling, and torque and moment are the same thing. Moment tends to be a better mathematical term to use to describe the way to calculate uh, these parameters. And this is a tendency of a force to cause rotation. And this is where we use the equation T equals FD perpendicular. All right, that's one equation that we'll use. Or the other equation we'll use with this is sum of torques acting about an axis equals the product of moment of inertia and angular acceleration, with moment of inertia being resistance to change angular motion. And I used this equation when I talked about isokinetics, okay? So there's two equations that we associate with torques or moments, and we can use either one. The sum of torque, usually we start by identifying that the torques acting about an axis, and then we add up all those torques, and that tells us the product of moment of inertia and angular acceleration. Angular acceleration having to be in units of radians per second squared. Moment of inertia is represented by how the mass is distributed about the axis of rotation. Angular momentum is just like momentum, but instead of mass times velocity, which is up here, this is quantity of angular motion, and it's moment of inertia times angular velocity. Now we spent some time, quite a bit of time on work, energy, and power. There it is. Work is, from a mechanical perspective, is an application of a force over some distance. And it shares the same set of units as energy, where energy is the capacity to do work. So these two terms go hand in hand, and we spent some time on the work energy theorem as well. When we start talking about the change in work done, we can understand the amount of energy it takes, things like that. Mechanical energy, a couple of examples of mechanical energy are listed here. Potential energy, that's the capacity to do work based upon position. And we use the equation mgh for that parameter. This is just one form of energy. And remember, energy comes in all different forms: chemical energy, nuclear energy, hydroelectrical, sound, all right? And in the mechanical world of energy, there's different forms of energy as well. Potential energy, kinetic energy, which is energy due to motion, 1/2 mv squared. These are just different forms of energy. We talked about spring energy as well, 1/2 kx squared. All right. And what happens in this work energy power approach to understanding movement, we need to understand how energy transforms from one form to another. Power is a term that mechanically is defined as rate of work done. So it's work over time. All right, and there's two equations that we use for that: work over delta T, or how fast the force is being applied. So force times velocity. Conceptually, this represents how fast we're transforming energy from one form to another. And sometimes that's from chemical to mechanical, or sometimes it's potential to kinetic, what have you. But it's how fast we're transforming energy from one form to another. And the equations are work over delta T, rate of work done, or force times velocity. Okay, air resistance force or drag force, these are the same things. Air resistance force is just a special case of drag force, and that the fluid that we're concerning ourselves with is air. I'll go to that in just a second. And buoyancy force is another force that that we spent time on in here. And for whatever reason, I don't have friction force in here. All right, that's another force that we spent some time on. I'll go through those in just a second. Newton's laws of motion, you need to know those. Just rote memorization. First law, an object will stay at rest when no forces are acting on it. It will stay in uniform motion, constant velocity, when there's no forces acting on it, or the net force is zero. The second law is law of acceleration, or when a force acts on an object, it will cause acceleration. F equals ma. And third law, for every force acting on an object, there's an equal and opposite force created by the object. But the critical aspect of Newton's second law is two critical aspects. One is we need to add up the forces acting on the object, and then we understand the product of mass, or inertia, resistance to change motion, and the acceleration of the center of mass of the object. Newton's third law says for every force acting on an object, there's an equal and opposite force created by the object, but we do not put the by forces in this equation, only the forces acting on the object. So that's really the key thing with using Newton's three laws of motion. Equations of constant acceleration, we really haven't spent any time on that in this class, but they're good to have in your back pocket because you never know when you need them. You know, we start talking about kinematics of the flight phase of running, for example. Those are all governed by equations of constant acceleration. In pressure, we spent a little bit of time on as related mostly to buoyancy force, but this is force per unit area. And so we did some videos specifically on that. And then friction force is just another example of a force that we give a special name to. And it represents how two surfaces are interacting with each other to ultimately prevent sliding or to stop an object from sliding. All right, but let me back up and just make sure we have the air resistance and buoyancy force down. The air resistance, the drag force equation is one that we really spent a lot of time on in this class. And drag force showed up in swimming, cycling, and running. But mostly swimming and cycling did we spend time on this. But this equation is 1/2 rho CdA V squared. And you should know each of the elements in this equation, and you should know the units, no matter if we're talking about drag force in the air, drag force in the water, whether we're talking about drag force propulsion or resistance, units are always going to be newtons. Any force is units of newtons. So rho is the density of the fluid moving over the object, all right? In the water, it's the density of the water. In the air, it's the density of the air. If it's salt water, it's a different density. If it's humid air, it's a different density. Or if we're in elevation, the density of air is different. So this is a quality of the fluid and air in this approach. Air is a fluid. It's considered a fluid. So density of the fluid. C, D, and A, we typically in the real on the field will combine these terms, but CD is coefficient of drag. Oops, CD is coefficient of drag, and it's how well the fluid moves over the object. And the easiest way I think about it is that side view of an object. In this case, this is like a wing. And if the air easily moves over the surface of the object, then we have a low coefficient of drag. If the air does not move easily over the object, like even around, we get some turbulence behind the object. All right. If the air does not move well over easily over the object, we'll get a higher CD. And there's other things that influence the CD other than just the shape of the object. It can be the surface of the object, how sticky the surface is to the fluid. All right. Sometimes you want to increase the CD, for example, swimming, you have a drag force that causes propulsion, and you want to have a higher CD. Sometimes you want it to be lower, cycling, and trying to go faster in cycling, you want to have a low CD. Now, A is frontal area. And in this case, we only look at a cross-sectional area perpendicular to the flow of the fluid. So if I was doing something like this, I'll actually just draw a line here, and I would just look at the object from the cross-sectional view where the fluid is moving right towards that object. Okay. And obviously, if the area that the fluid is hitting the object is bigger, then in this case, that's going to cause a greater drag force. This is the same thing as sticking your hand out the window and having your hand push against the air versus tilting your hand and having the hand easily move through the air. The frontal area of the hand this way versus this way is bigger. This is bigger than that. So the drag force is related to that frontal area. Right? But a lot of times, sometimes these two are hard to separate from each other. So we'll collectively refer to them. Why am I doing that? CDA. We're collectively, it's two terms, but we'll often combine them. And it's a little easier to measure these together as opposed to independent from each other. And then the last term is V, and this is really the one that sort of gets people. This is the velocity of the fluid moving over the object. It's not necessarily how fast the person's going, not how fast they're swimming, not how fast they're cycling, how fast they're running. All right, but it's how fast the fluid is moving over the object. So obviously it has to do with, wind speed or current speed. And the direction of the wind pushing on the person. Sometimes what we do is we think about a situation where the person's moving in a controlled environment where there is not any wind, and then we can use this V to represent the velocity of the person. But we have to be really careful that we understand that the V in this equation is velocity of the fluid. All right, and then the other term, so again, drag force showed up in each of our sports, so you really want to know that equation. And the other equation that we spent some time on is the buoyancy force equation. Remember, buoyancy force is the upward directed force due to the object being in the water or in a fluid, sorry. And the way that we experimentally determine buoyancy force is the weight of water displaced. And I showed some videos of how we determine the buoyancy force of some wetsuits. We submerge the wetsuits and we measure the amount of fluid, the amount of water displaced by the wetsuits. And a wetsuit that has a greater buoyancy force displaced more water. The equation for buoyancy force is rho g v, where rho is again the density of the fluid, g is the acceleration due to the force of gravity, and v is the volume of fluid displaced. Acceleration due to the force of gravity. Okay, always get a little, we don't say g is gravity. That's the acceleration due to the force of gravity. All right, and again, this has units of newtons because it's a force. Looking for a new marker, and this is that. The weight of the fluid, or in the case of the wetsuit and what I showed there, the weight of the water displaced. That's all that is. All right, so it all goes hand in hand with our force. All right, those were the key equations, and then there's some other things that we've done where we looked at velocity of running is equal to the product of stride length and stride frequency. That equation is good to know. I mean, that's something that we understand for both swimming where this would be stroke length and stroke frequency, and running. This would be stride length and stride frequency. So that's also good to know. So those are equations. Those are the key ones that we dealt with, both from the terminology worksheet and just a little bit more details on the drag force and buoyancy force. Okay, know your equations. A lot of the questions on the final exam are predicated on you knowing these terms. The question won't always be which is the definition for angular acceleration. But instead it will be angular acceleration is this. Now, what do you know about torque or something like that? So you have to know these terms in order to answer some of the questions. Okay, I hope that helps. And level 1, know your terminology. Okay, thanks.